So in the last video, I showed you the solutions for the confidence intervals of the slope, intercept, and regression line. In this video, I'd like to derive how we got those solutions. So before I proceed, let's talk about some definitions just to make sure we're very clear with these variables. Okay, so y, I, and xi are again our pairs of data. X hat and y hat are the mean values of our data values. And m is our vector of model coefficients. In this case, it's the slope and intercept. This y sub mi is our model line. And we can write that in vector form as ym is equal to our A matrix times m, representing the model line for all our values of x, all n values of x. Our error vector is the difference between our model values and the measured values of y. So that's ym minus y. And the that so the model values or our model line is contrasted with the true linear trend that influences our data. And the parameters there are alpha 1 and alpha 2. Again, those are estimated by A1 and A2. And right, so our data is the sum of this true line plus everything, all the natural processes or errors in our measurements that are not related to the true linear trend. And this is our noise. Okay, and this is our true deviation from the true linear trend. Now, the variance of each measurement of y is described as sigma squared sub I. And again, in this case, we're going to assume that the variance is the same for all our measurement points. So we'll just refer to this as sigma squared. And again, we've assumed that x is known perfectly. So so the variance in the model line is 0. Okay, there's no uncertainty in x here. So the variance at each point, each measurement point of y is completely due to the variance in our noise. So the variance of y at point I is equal to the variance of the noise at point I. We don't know that noise, we don't know that variance, but we can estimate it by taking the sum of square misfits. And I'm noticing I need to, instead of n minus 1, I need to divide by n minus 2. And the variance of our intercept, we can write that as VAR of our intercept, or we can equally write that as sigma squared sub A. Likewise for our slope. And I'll also introduce that there's a covariance between our slope and intercept. These two, the solutions of these two are dependent both on the same values of x. So there is a correlation, there's a covariance between those two uh, estimates of the slope and intercept. So before we get right into deriving how we define these variances, I'd like to show you a little bit of background, a little bit more background about the solution for our line fit. Okay, so we found our solution by our model vector equal by applying our linear least square regression solution, which was our matrix A transpose A inverse times A transpose Y. Okay, and let's look at A transpose A. That was a row of ones and a row of our x values. That's A transpose. And A was a column vector of ones, and our values of x in the next column. And when we multiply that out, we have a 2 by n vector times an n by 2 vector. We get a 2 by 2 vector. Sorry, we have a 2 by n matrix and an n by 2 matrix. And so we'll get a 2 by 2 matrix. And the first component is n for multiplying 1 n times and summing. And the next is 1s times all the values of x summed. And this component is our vector of x's times 1s, again summed. And then the last component of our 2 by 2 matrix is all the x values multiplied by itself and summed. So that's A transpose A. So now let's look at the inverse matrix. And let me look at this part up here. Okay, so in general, so if we have a matrix capital M of A, B, C, and D, for example, and this is the inverse, I'm going to show you the inverse of a 2 by 2 matrix, then M inverse is equal to D, so the opposite diagonal in the first component, over the determinant D. We have minus B over the determinant in the next component, minus C over D, the determinant, and then A over the determinant. And that's the inverse of matrix M. So with A defined above, or sorry, A transpose A defined above, the inverse of that is equal to the sum of x squareds divided by the determinant. And the determinant, let's look at the determinant of A transpose. The determinant is n times the sum of square values of x's, right? We have to multiply these two diagonal components minus the product of the off diagonal terms. And with a little bit of algebra, you can show that this is equal to n, not m, n times the sum of square deviations of x from its mean. And when I write the sigma, the sum of I from 1 to n is implied. I'm not going to write that every time, but that is what is implied. So the determinant is n times the sum of the square deviations from the mean. Okay. And the next term is the sum of x's divided by the determinant. So it's also divided by n. So the sum of all the x values divided by n is the mean value of x. And then the remaining part of the determinant is the sum of square deviations from the mean. And there's a minus sign there. The other term on the opposite corner has the same value. And then the last term is n divided by the determinant. So and remember, n is part of the determinant, so the two n's cancel and we're just left with the sum of square deviations of x from its mean. Okay, so that is the inverse of A transpose A. And I'm showing this for a couple of reasons. The second of which we'll talk about later, but the first of which is for you to see that the model coefficients, remember M was A1 and A2, those solutions are going to be functions of these sums. So the solution for slope A2, that is the slope that yields the least square misfit, is the sum of the deviation of x from its mean times the deviation of y from its mean all over the sum of squared deviations of x from its mean. And the solution for the intercept is simply the mean value of y minus the slope a2 times the mean value of x. Or in other words, the mean value of y is simply equal to the intercept plus the slope times the mean value of x. Okay, let's now we're ready to finally derive the variance for A2 now that we've seen I've given you some background of where the solutions for these parameters come from. So the variance of A2, right, comes from knowing that A2 is a sum of functions of xi and yi. And so the variant, or actually, well, if we talk about an error of A squared, that's going to be an error associated with all those functions, right, for each value of I. And remember, x is assumed to be known perfectly, so all the error associated with f is due to y. So we can write that square error as the partial derivative of f with respect to each value of y times the uncertainty or error of y. And those are both squared. And again, so this is the sum of errors for n independent values of y. So these are independent measurements of y. And so we can write a similar equation for the variance of A2 is equal to the sum of df dy2 times the variance of yi. Okay. So the square of the partial derivative of f with respect to yi. So we just have to take this derivative with respect to yi, and we get xi minus its mean all over the sum of the square deviations of x from its mean. And we have to square this. So we square the numerator and the denominator here. And then the variance of A2 is the sum of all that times the sigma I2, the deviation of each measurement from, again, the regression line, right? Because that's our estimate for, right. So the deviation of y from the regression line is delta yi, or sigma sub I guess in the previous, I should use sigma squared I. And then we have the sum of square deviations from x from its mean, all to the fourth power. And again, if we assume that the variance at each point of y from the linear trend is the same for all points, then we can bring sigma on the outside of the sum, sigma squared on the outside of the sum, and we notice that, well, we can divide out one of the sum of squared deviations from the numerator and the denominator. And that's our solution for the variance. And the solution for the standard deviation, as I wrote out before, is simply sigma divided by the square root of the sum of square deviations of x from its mean. So that was the derivation of the variance of the slope. Now let's talk about the variance of the intercept. So this is our equation for the intercept, and we know that uncertainties in A1 squared is equal to by using the rule of sums for errors, we know that that's equal to the uncertainty of the mean y value squared plus the uncertainty of A2 times x hat squared. Or in other words, the variance of A1 squared, variance of A1, sigma A1 squared, is equal to the variance of y hat plus the variance of A2 times the mean value of x squared. And the reason we're only concerned with the variance of the slope is because, again, x is known perfectly, so we know the mean location of our data points well. So recall that the variance in y is only due to the noise about the variance of our mean of y. So so we measure our data values of y and we calculate the mean. The variance of that is only due to the dispersion or the variation about the true linear trend. So that variance is simply sigma divided by n. We have to sigma squared divided by n. So recall that as we sample from a population, the variance of the mean of that sample is inversely proportional to the size of our sample. So that's 1 over n. And then we have the variance of our slope, which is sigma squared divided by the sum of our squared deviations of x from its mean. And this gives the variance of A1 is equal to sigma squared times 1 over n plus 1 over the sum of the square deviation of x from its mean. And we can show, I won't, but you could show with a little bit of algebra that we can perform this sum by finding the common denominator, and the solution we get is sigma squared times the sum of xi squared all over the sum of square deviation of x from the mean. Okay, so that's the variance of our intercept, and then the corresponding standard deviation is just the square root of that. Oh, and I'm noticing I'm forgetting the n on the denominator. We need an n there. So now it turns out that we can write these solutions in matrix form as the variance of our model parameters, and this turns out to be a matrix. Okay, that's equal to sigma a1 squared, and the covariance of a1 a2, and then we have the variance of the slope in the other diagonal, and that is equal to the sum of xi squared. I'm writing the solution I just wrote for the variance of a1, and then the solution for the variance of a2, there should be a 2 there, is 1 over the sum of xi minus its mean squared, and that was multiplied by sigma squared. And the covariance turns out to be the mean value of x divided by xi minus its mean, the sum of that squared, and then we have x hat divided by the same sum. And the reason I'm writing this in matrix form is it turns out to be quite easy to solve, for example, in MATLAB, because this matrix is simply A transpose A inverse. Okay, and so the other reason I wrote this out in matrix form is the variance of M written this way is true for all general least square regressions. It's not specific to a line. This is true for all basis functions, whether it be lines, polynomials, or other functions. So this is a powerful way to quantify the variances of the model parameters. And last but not least, let's derive the variance of the regression line itself. Right, so remember our model line, our regression line is y sub mi, and that's equal to a1 plus a2 times xi. And we know our solution for a1 is the mean value of y minus a2 times the mean value of x. And so ymi can be expressed as the mean value plus the slope of xi minus its times xi minus its mean value. Okay, so we want to calculate the variance of that. So the variance of ymi is simply the sum of the variance of each of these terms. So that's the variance of the mean value of y plus the variance of a2, the slope, times xi minus x bar squared. Again, this term does not vary because we're assuming we know x perfectly. And so we know the variance of the mean value of y is sigma squared, again, divided by n. And we know the variance of a2 is sigma squared divided by the sum of xi minus its mean squared. And we have xi minus x hat squared. And to be consistent with what I wrote before, I'm going to sum over k in the denominator, just to make it clear that this sum is carried out, and this carried out already for the denominator, and this k is different from this I. And so the variance of each point of our regression is equal to sigma squared times 1 over n plus the deviation of each point of x from its mean squared divided by that sum again. And this is the solution I showed before. Actually, I showed you the standard deviation, but you just take the square root of this whole thing to get the standard deviation, of course. And so the confidence interval on the true trend is simply the model trend plus and minus the standard deviation of the model trend times our value of t. Right? And so what you'll notice is the standard deviation, or the variance of the model trend, is a function of x, and it's a function of it increases as the deviation from the mean increases. So you can see in the solution that I plotted in this example for our 4 Hawaiian volcanoes, that the standard deviation is smallest near the mean, and it tends to increase with distance in x away from the mean. So that's why these dash curves get wider away from the middle of this plot. And finally, to close, I'd like to just write that out, the variance of a regression line in terms of matrices. So again, ymi is equal to a1 plus a2 xi. And we can write that out as ymi is equal to the ith row of A times the model parameters, which contain, again, so the model vector is the vector of A1, A2, And I better write this as transpose because this is a row vector. It's the ith row of A. And using our top equation to define our variance, the variance of YMI is equal to the variance of A1. Before we use the solutions for A1 and A2, but here we're actually using A1 and A2 to define the variance. And because A1 and A2 are not independent, we have to take the covariance of A1 and A2, and we have to multiply that by xi. And then the last term is the variance of A2 times xi squared. And we can write that in matrix form using the matrices that I just defined. Like that. And in matrix form, that becomes the ith row of A. We denoted that as A transpose sub I. And this whole term is simply A transpose A inverse times sigma squared, and then we have a I. So this is the matrix form of the variance of our regression function at each point of I along our regression curve. And the advantage of using this form is, well, this is a one-line typed code in MATLAB, but it's also true for general least square regression for any basis function. In the case we've just used, where we're dealing with a line, the basis functions were a constant and x for a line, but they could be polynomial functions or any basis functions. And we can use this matrix equation as long as A is defined, and we can estimate sigma squared. So to write this out in MATLAB, I would write a for loop because the variance of ym at each value of y must be defined. And the first row, or the ith row of A, is A written as I've shown here, the ith row for all the columns of A. And A, of course, was already defined because we would have already done the solved the least square problem already, because now we're just looking at the confidence intervals. And then we take the inverse of A transpose A, multiply that by the row of A, but we have to multiply that, we have to take the transpose of that to carry out the multiplication. And we have our estimate for the variance of y about the linear trend or the regression trend. So that's how you would do that in MATLAB. That would give you the variance of each point. At each point of our regression line, you multiply that by the appropriate t-value and add or subtract it to the best fitting line. And this is how you draw these dashed curves. Okay, well, that's enough for this video, so I will conclude.